taking advanced calculus, is very, very clear. In fact, you probably have to memorize it. So that's what we're used to. And that's the way it should be. So it's really awkward. I talked to Dr. Jones today about this, asking him, what is this definition? Because I Google searched it, couldn't find it anywhere, and he told me, you know, it's just not well done. Okay, so at least it wasn't just me. And you'll see what I mean in a second. At least it's not that weird color today. So what I wanted to do was to go through and make some of the material on dots and boxes more rigorous, have it proved, and understand it, and really understand where they came up with the idea of chains. And you'll find out today why they use the word chains, because they're transforming the dots and boxes game to a different game. And that's called strings and coins. So the way you do the mapping from boxes and dots and boxes is the boxes, every box that you can make becomes a coin. I'll show you what I mean. So if I have a 4x4 dots and boxes palette, so just about to play, this is the thing you see when you go on the computer, a little bit nicer looking than that, you see this thing. So how you make the transformation is, for every box, you put a coin. So the yellow represents coins. So I have 3 boxes on top. The second row has another 3 boxes, and the third row has another 3 boxes. And what I do from those 3 rows of coins is I put strings on every coin. So this coin right here has 1, 2, 3, 4 strings attached to it. So each coin has 4 strings attached to it. Adding a side, so I just added a side right here on dots. That's how we play, right? We make lines on the dots and then try to form boxes. So adding a side is equivalent to taking away a string. So if I do this, for example, and it goes clockwise. So what happened here is I put this line here. That string over there got removed. That's where this line corresponds to that string. This line down here corresponds to this string. So that gets removed. So adding lines and dots and boxes is equivalent to removing strings from the string and coin game. Now I'm going to add this bottom line down here. That's equivalent to that one. And when I finish the box, what happens? Where do you think that one's going to come from? The last one over here. So I'm going to remove it. Forming a box is the same thing as having a standalone coin. So the way you play strings and coins is you remove or cut strings, and when a coin has no strings attached to it, that player removes that coin. So in this case, it took me 4 times around to get the box. So player 1, player 2, player 3, player 1, player 2. So it's player 2's coin. Player 2 would take it. Notice everything matches, everything maps. So I formulated this line down at the bottom, and this corresponds to the box below it. It's the top of the box below it. It's also the string that attached to the coin below it. So there's a mapping. It's a map. What annoys me is there's no formulation of the map in your book. And I spent a few hours trying to just troll the web thinking somebody has written this somewhere, and nobody has written it anywhere. If you look at any of these definitions that they're talking about, they talk about just as loosely as in your book. So that's what I thought, okay, remember I told you, mathematician, bravery and patience. I'm going to be brave enough to take the charge and do it myself. So you're going to get more formal language as we move along. So in this way, we've transformed dots and boxes to strings and coins. And the reason I was looking for a nice formal language is, how many of you are taking the abstract algebra course right now? Anybody? How many of you took it? Okay, so you took it. So you talked about things like isomorphisms, and you talked about homomorphisms. Do you know what that was all about? Were they definitions in the book that you had to memorize? What was that about? Not really sure? So this is a great example of what it's about. So the way they're going to prove things about dots and boxes is to go to strings and coins, because using strings and coins is going to be a lot easier to visualize what's happening. Any move that you make on the strings and coins has an equivalent move to the dots and boxes. It's really the same game. There's a map that corresponds from one to the other. So it's like two different planets, but there's a code book from one to the other, a dictionary. Every move over here has a corresponding move over here. So you don't have to work in the dots and boxes world anymore. You can work with the strings and coins world. Any proof you have, any theorem you have on the strings and coins translates back to the dots and boxes. So that's the kind of map that you used to work with in abstract algebra. That's the whole point. So if you have an isomorphism from one group to another group, it really means you probably got at least that they were the same group in some way. Hey, you want to sit in my class today? Yes. I'm not as good as you. I'm sorry. So you get this kind of translation between the two. And I don't know. Yeah, you did. You did have problems in your book. What book did you guys use? Fraley? Galleon? The white one's Fraley. So you had problems in your book where you had to say, look, if there were n, the order of this one was n, then the order of that one was n. So that's a theorem that says that if you have an isomorphism between two groups, then the number of elements here are equal to the number of elements here. You've proved a theorem in one world, it's equivalent to the theorem in the other world. So anything that you do on the one means the same in the other. And this one's a little bit more easier to understand because we have a reason for doing it, because we want to prove who's going to be the one who wins and how can we best win. The optimal strategy. So I wanted to go through this again so that you could see a little bit more, because it took me a while from reading the book to figure out what they were doing. So here's a string and coin game, and I just played it so you could see how to play it. So what I did is I went down to the bottom here and I removed a string in Paint. Very sophisticated tool. So then I went through again and I just removed another string right over here. See that? And then I removed another string over here. And then I removed another string. Where did I remove it? Oh, maybe I didn't remove another string. Let me see. Might have just copied and pasted it. So there, I removed the final string, which is right here. And the object of the game is to remove strings so that you can grab the coin. And so the next move would be to take that coin. And it's same rules as dots and boxes. If I remove a coin, I get to go again. Well, get to. It's probably impediment. Yeah. So you go again. You have to go again is probably the way you say it. So if this was a aberration right here, we have first player, second player, first player, second player, first player. In this case, the first player wins this box or this coin because they got to remove it. They have pictures in your book where they're trying to explain the equivalence of the two. This was a picture that I took from your book. They're trying to draw it and explain it to you. I thought it would be easier if you had an array. I actually don't know why we have to write books the way we used to. We could actually do the books like videos, right? Just like I'm doing right here, you could do a video book. You don't have to do it this way, and then you can see the animation. I actually thought, wouldn't that be great? Because sometimes I have to write papers, and for some reason they want to know how something works in the math when they're not a math person. And I thought if they just gave me chalk and a blackboard, I could really explain it. And I thought, wait a minute, I have chalk and a blackboard. I'm doing it in class. So, you know, and I started doing that with researchers I work with. I start scrapping out the math in animation, and they love it when I send it to them. So why can't books be like this? There's a video book. Has to be a really good teacher, though, right? It has to be somebody used to doing this. Online classes are a little bit like that, but it would make it much more clear. All right, so what they did is they showed you that the formation of this box down here with the label A in it is the same as that standalone A coin that's there, again showing the equivalence. And that forming that line is the same thing as deleting that string. So that's what they're trying to illustrate to you. It's much easier to see that animated. So the point of this is we can move to strings and coins instead of moving to boxes. So I didn't have time to explore this, but during my frantic Google search for the actual rigorous definitions, you can try looking for it. If you find it, let me know. But I noticed that the strings and the coins, it's graph theory. And some of the language that they might be using might be borrowed from graph theory. John Cutler's office was dark. I didn't get a chance to talk to him, but I intend to ask him, first of all, what some of these things are, what the rigorous definitions are, because they're not in our book. And I'm highly irritated by it if it doesn't show. So I have questions for you to think about. If you're going to graduate school, these are the kind of questions you want to think about as a math person that wants to continue a career in math. In abstract algebra, not just abstract algebra, if you go further enough in advanced calculus, you talk about maps all the time. In fact, what are you guys learning about in advanced calculus? Convergence, okay? So that tells you what that class is about. It is about limits. If I had one word to describe advanced calculus, it's about limits. And if I had one word to describe what, or two words, to describe what algebra is, abstract algebra, it's about solving equations. Solving for roots of equations, actually. That's what those two classes are about, ultimately. So what do you want to preserve in abstract algebra? You would like to preserve, if I solve equations in this world, then I would want the same corresponding equations to be solved in this world. And that's what you use isomorphisms for, ultimately. Ultimately, that's what you're using it for, that you're trying to solve equations in this easier world over here, and you want a translation to solving equations in the other world. In advanced calculus, the class is about limits. So you talk about maps that preserve taking limits. Taking limits in this world over here is the same thing as taking limits over here, and they call that isometric. Isometric maps. It's always an iso. So here's questions I want to ask you. Isometric and isomorphism have some commonalities. One is you have one-to-one, you know. That one-to-oneness means that if you have two worlds, well, the guy over here in this world has to have a corresponding brother over here in this world. So there's got to be a one-to-one map between the two. And the onto-ness means that, well, it really boils down to in finite things that you have the same amount of people in that world as this world. It really means that if there's a guy in this world over here that you randomly pulled out, you can find his brother over in this world. That's what onto means. Won't fly in Dr. Brzezinski's class, but that's what it means. You know, there's a formal definition, and then that's what intuitively what it means. That's what it means. So don't be writing things like, you know, the guy and his brother in Dr. Brzezinski's class. He's gonna be calling what's that place called? CAPS, the place that gives you psychological help, counseling. I have a student talking about different planets and worlds and brothers. And all I asked him was, what's the definition of an isomorphism? So think about that for extra. If you are going to graduate school, this is a small enough class, you'll never confide in me again. I want to know the answer. So I'll pick on you. Where's he? Your corresponding brother is not here today. Tell him to watch the videos. Yeah, because I'm going to ask him. So is that map one-to-one and onto? So what I want you to do, it took me some pain to kind of read through the book and figure it out. I want you to actually try it. Start with a 4x4 dots and boxes palette. Play the game of dots and boxes, but next to it have your dots and boxes palette drawn up here, and right next to it have the string and coins drawn up here. And actually make your moves. You can even do it with two players, have each player take a turn. Every time you take a turn on the dots and boxes, then go over to the strings and coins and make the corresponding move on the strings and coins. Just play the game, transferring your dots and boxes to strings and coins, and you have to show me the work because I have to see that you got the idea. So don't worry about who wins and who doesn't win. Just play the game on, with
someone wins.
Someone has to win, right?
Yeah.
If someone doesn't win, then we have more problems than just is the map one-to-one and onto.
So you have to draw.